Patches or like improve the coverage of your simulation. Now you're running a lot of these random tests. A lot of them are not adding to your coverage, but they're being generated, being simulated. You're wasting a lot of time. So the idea here is to try to develop something that, as we say here, a novel test detector, something that, if you can imagine, can tell you, can predict, look at the test before I simulate it and I waste my effort, can tell me, okay, this is no good, this is not useful, throw it away, before you simulate it actually, okay? But that will speed up things, okay, because I'll be throwing away some of these not useful tests before actually I simulate them. So how do we do that? Well, we do that by actually analyzing the results of some of the tests that you already simulated and trying to learn from the data that that was generated, what makes a test useful or potentially useful, okay? And try to apply, or actually, what makes a test not useful? Okay, both coins, sides of the coin are useful. And use that knowledge to kind of throw away a lot of the tests before you simulate them. So basically, you will generate a lot, but you will only simulate few. And hopefully the ones you simulate are the ones that are beneficial, okay? So and even more, if you become very kind of smart, one day you can actually, learning more about what's a good test, maybe we can generate more of these good tests, okay? So once we become very kind of, oh, a good test should have this characteristic and this characteristic, and I need this and I need that, I can go and actually tweak this program that's randomly generating them to make it a little smarter in generating good ones faster. Okay, so typically when you do simulation, this kind of depicts the picture. You simulate what's being displayed here is the simulation of the test, okay, and the number of the tests you simulated, and here is the coverage. And as you can see, kind of the coverage, at the beginning, you're kind of going up, and then you get into these regions where I'm simulating a lot, but the coverage is not improving. So there's a lot of this, as we said, the wasteful simulations. And this is one design called CFU, another design, LSU, okay, different sizes, and each one of the tests is actually, I wanted to highlight this, when I say a test, it's not actually a simple, like a binary test. It's a little like assembly program. These are complex designs. So a single test can be about 50 random instructions that are kind of pieced together to make a little assembly program. That's a test. That's a test that needs to be simulated. So. So it kind of, the same phenomena is repeating, okay, on the different circuits. You get some very good coverage very quickly, then you kind of slows down, then I get one good test and a jump, and then nothing happens for a while, and then another good test. And gee, we ask ourselves, can we generate these good ones and not waste our time with the stuff in between? And here's the results on one of the, it's actually maybe harder to see on this slide here, but you see that little green line, okay, at the very, very beginning? That's actually after you apply what I just showed you earlier, okay? What happens, okay, is that you can apply a few hundred tests, you can get the same coverage instead of running these 10,000 tests that we were doing earlier. So massive speed ups, 300 instead of 10,000. Actually, we can stop the simulation around 6,000, okay, if we do it the old way. With novelty detection, you can only simulate 310 tests. Again, using data mining was used to learn what's a novel test and what's not, and to try and throw away all the tests that are not novel. This is also results on the second example. The red shows the same kind of phenomenon. And test template refinement has to do with trying to make the test generator generate more novel tests, targeting very specific coverage problems that we have not been able to hit before. That's a very, very powerful. In fact, this is lots of people are interested in that because the test generation or simulation problem, what people typically do is that they run these random things for a while, and then you see there's a coverage gap still that they couldn't hit. And what do you do now? What you do now is you have some very smart engineers. They try to generate manually programs to hit these things. And that can take significant amount of time. So here you are kind of about to tape out your chip. You don't have enough coverage, and you're waiting for the coverage to get up before you can go. So this kind of addresses this problem. So here we're going to learn from both the novel tests that we have seen and the non-novel tests, the one that are not useful. We're going to learn what makes things novel and what things makes things not novel, as I said earlier, and then use that to generate different types of constraints that can be used by the random test generators to generate better novel tests. So trying to kind of illustrate here, to try to learn what makes novel tests are special. I think I have an example coming up. And the amazing thing here is obviously now by applying this, I'm getting higher coverage than the original, what we were able to get, okay? Because now we're generating newer tests that were not there before. The third kind of related area is what we call assertion coverage. In assertion coverage, you try to hit, assertion is one type of this condition that you try to hit these conditions, and you may be running a lot of simulation, but you never get this condition satisfied. So an assertion is if the queue is full and this bus is in this mode and this and so on, okay, and if these conditions don't never fire, we say you still have a hole in your coverage because you never experience this thing that will happen sometime during the real use of that device, and you have not figured whether it actually works or not under that mode. So assertion coverage is very important because it relates to things that will actually happen or could happen in the real use of these devices. So it's very important to hit them, and if you don't hit them, you kind of, you never know what's going to happen in real life. So to try to kind of, if you look at your simulation results, you may discover that some of these assertions we come close to hitting it, but it doesn't fire all the way, or we have very few tests that actually cause them to fire, not enough to claim that we have good coverage. So here's an example. We had 3 assertions that the original 1,000 tests have only fired one of the assertions 3 times, and 2 of the assertions were not exercised. And by deploying this knowledge and rule learning technique and improving the random generation, we were able to generate 200 more tests, and these hit assertion A 33 times. What happened, assertion B and C turned out to be very related to A, correlated with it. And as we increase the coverage for A, luckily, we got assertion B and assertion C to fire. This is not something guaranteed, but it was a true phenomenon that by improving the coverage for assertion A, we just all of a sudden we were able to hit B and C. And you can iterate over this because now you have some actual tests that can